The first law of photochemistry states that light must be absorbed for photochemistry to occur. This is a very simple concept, but it is the basis for performing photobiological experiments correctly. Since photobiological and phototherapeutic effects are initiated by photochemistry, unless light of a particular wavelength is absorbed by a system, no photochemistry will occur and no photobiological results will be obtained, no matter how long you irradiate with that wavelength. A significant number of papers on LED phototherapy, laser and LED phototherapy, would not have been published if the authors and the reviewers had known the first law of photochemistry. And now for a word of caution. You should not believe everything that you read. Just because it's published in a book, it does not make it true. Many of you know that I started the American Society for Photobiology 37 years ago, but I bet none of you know that I'm also considered to be the father of all of photochemistry. It must be true. It's in the book. According to what is known as Kendric Smith's first law of photochemistry, light must be absorbed for photochemistry to occur. Not only do they have it wrong about the first law of photochemistry, they also misspell my name. There's no K at the end of Kendric. Unfortunately, there are a lot of errors in this book. The first law of photochemistry has been around since the 1800s. Actually, it is known as the Grotius-Draper law, not the Kendrick-Smith law. Low-level light therapy is real and beneficial, and I get very upset when people publish false statements or perform bad science and photobiology. Until the LLT field gets rid of bad science and bad photobiology and falsehoods that are published, LLT will continue to be considered snake oil medicine by most qualified scientists and physicians. Now back to science. There are two other laws of photochemistry that should be mentioned for the sake of completeness, even though they have little relevance to phototherapy. The second law of photochemistry states that for each photon of light absorbed by a chemical system, only one molecule is activated for a photochemical reaction. This law is true for ordinary light intensities. However, with high-powered lasers, two photon reactions can occur. However, two photon reactions are not important for LLT. Another law, the Bunsen-Roscoe law of reciprocity, states that a photochemical effect is directly proportional to the total energy dose, irrespective of the time required to deliver the dose. This law is true for chemicals in a test tube, but the response of cells to radiation usually involves a sequence of interacting biological reactions, making linear dose times time relationships highly unlikely. For example, giving a total UV radiation dose to cells all at once kills many more cells than the same dose when fractionated. DNA repair systems are induced and by the first irradiation, and they have a chance to repair the damage produced by the first irradiation before the next irradiation. There is no reciprocity for when damage is produced and repaired, but there is reciprocity over a very narrow range of doses for photoreceptors that trigger a response, such as phytochrome in plants. The relevancy of reciprocity to LLT remains to be demonstrated. Absorption spectrum is a plot of the probability that light of a given wavelength will be absorbed by the system under investigation. Because of its unique electronic structure, each chemical compound has a different absorption spectrum. Each of the wavelengths absorbed by a chemical compound will be absorbed to different degrees, again because of the unique electronic structure of that particular molecule. Therefore, an absorption spectrum of a compound that one is interested in will immediately tell you the optimum wavelength to use to obtain the maximum absorption with the least amount of radiation. Of course, not all of light energy that is absorbed will produce a chemical effect, since some of the absorbed energy is, whereas light's given off as heat, as the electrons fall to lower energy levels, and it's all energy can also be given off by lower energy light, such as the phosphorescence and fluorescence, to get the electrons back to their ground state. Once a photobiological response is observed, the next step should be to determine the optimum wavelength and dose of radiation to produce the effect. That is, an action spectrum. An action spectrum is a plot of the relative effectiveness of different wavelengths of light in causing a particular biological response. Under ideal conditions, it should mimic the absorption spectrum of the molecule that is absorbing the light and whose photochemical alteration causes the biological effect. Thus, an action spectrum not only identifies the wavelengths that will have the maximum effect with the least dose of radiation, it also helps to identify the target of the radiation. For example, the action spectrum for the killing of bacteria mimics the absorption spectrum of DNA. This result is quite understandable in view of the extreme importance of DNA to a cell. These results tell us that if you want to inactivate DNA with the greatest efficiency, that is, with the least dose of radiation, you should use the wavelength at the peak of the absorption and action spectrum. Think of different wavelengths of light as different drugs. Therefore, it is important to establish which drug is best and also the optimum dose. Dr. Tina Carew has provided us with many action spectra. These are those that she has provided for growth and DNA and RNA synthesis. And you can see that she's already talked about these over here that correspond with the copper in cytochrome C oxidase. And they suggest certain wavelengths of light that are optimum for LLT. She mentioned 400, 620, 680, 760, and 820. This action spectrum is not as easy to interpret as the one I showed you for the killing of bacteria. However, some of these peaks are identifiable with cytochrome C oxidase, which resides in the mitochondria. You will note, however, that there are a lot of valleys where the wavelengths are not as effective per unit dose. Using a wavelength in one of these valleys might produce the effect you want, but the dose necessary to produce the effect might be so high that unwanted side effects would probably be produced. You can see a nice review by Dr. Carew on action spectra on the website, Photobiological Sciences Online, an online textbook on photobiology. There are other papers there on low-level light therapy, as well as papers on all other areas of photobiology. Determining an action spectrum is a very difficult endeavor, but I wish that someone would do action spectra for some of the clinical effects that are being studied now with random protocols. Then we would finally have a scientifically based protocol for treating patients, and the reputation of LLT would soar.